The things we're going to start with is so-called the spontaneous process. Thermodynamics is a subject that got intensively investigated by scientists around 200 years ago. And then one thing that feel very curiously is actually certain process happen actually unidirectionally. For example, if you put the ice on the table at room temperature, the ice will melt spontaneously. And then the salt dissociation thing is actually spontaneous too. If you throw sodium chloride into water, after some time, they all disappear, they dissolved. So the dissociation of your sodium chloride thing is spontaneous. So from there, after 200 years carefully observation, scientists realized that some things actually can happen unidirectionally. Then they define the things they see this behavior, okay, as a spontaneous process. Let's start to think about, okay, why certain process happens spontaneously. Can we actually find some parameters? If we can calculate the parameters, then we can predict the process can happen spontaneously. The first parameter is something you already know, the entropy. So we actually calculate the entropy of a reaction many times in your Jenkins 1. And then typically, if your delta H is negative, then it's actually it is a exothermic reaction, then probably it will be spontaneous. Okay, so that's actually the wrong concept people had long time ago, because later on they realized they observe both reactions can happen spontaneously, regardless the delta H is positive or negative. Starting from there, they think about, okay, so delta H alone apparently is actually not a good parameter to use to predict whether the reaction is spontaneous or not. So they look very hard. Eventually, scientists actually identify another term called the entropy, delta S, to predict whether a reaction can happen spontaneous or not. So in the end, they realize, okay, it is not just delta H, okay, it has to be the overall effect of your enthalpy and the entropy. Okay, if you consider both of them together, then you can have a unified way to predict whether a reaction can happen spontaneous or not. So these things was actually eventually connected through a term called the free energy. So free energy is eventually the terms that scientists use to predict whether reaction can happen spontaneous or not. Okay, we're going to talk about the details later. But before we jump into the free energy, we want to actually introduce a few terms. So the first term we want to introduce you is called the system and the surrounding. Where the combination of two, we call it universe. So universe is a combination of system and surrounding. We want to know what is system, what is surrounding. Assuming today you're actually doing a chemical reaction. So for most of the time, what you do is actually you have a beaker or flask. Then you're going to put in your reactants. Let's say we put the sodium chloride into water to form the solution. Then we will call these things as our system. And then all the other things, we will call it as surrounding. So I use this rectangle to represent anything else. That is actually your surrounding. And the sum of your system and surrounding, we call it as universe. So this whole thing is your universe. So for the system can be anything of your interest. You can define anything as your system. But once you define your system, anything outside your system is called the surrounding. And the sum of the two is the universe. Okay, so that's actually a very important concept that you should know. What scientists found is actually if you can calculate the entropy of your universe, okay, it's not the entropy of your system, it's not the entropy of your surrounding, but the entropy of the universe. If you calculate that, although we don't know how to calculate that yet, okay, but you'll learn how to calculate later, okay? If you can calculate your delta S universe, and then if that delta S universe is larger than 0, then you can have spontaneous process. If the delta S universe larger than 0, then you're going to have spontaneous process. Be careful, it's not delta S system, it's not delta S surrounding. It has to be delta S universe. If the delta S universe is larger than 0, then you have spontaneous reaction. Before we move on, one thing I want to actually mention is that, okay, so what is entropy? What is this? So if you look at your textbook, you will see the entropy probably was defined as the randomness of your system. So what is randomness? Why the nature likes to have a larger randomness? Have you ever think about these problems? This is actually one of the most important concepts that humans create. We realize that nature like random. How those little things actually connect to the chemistry we're actually learning. So every time when you see the textbook say, okay, it's more random, what does it mean? So this rule is actually all about dissipating the energy. What is energy? It's a very abstract concept, right? So even though you've heard this term energy a lot, it's not something you can always see. Heat is one form of energy. What other forms of energy you can think of? Is light a type of energy? Okay, it's a form of energy, right? So in nature, okay, if you have a substance, okay, the substance will always trying to find the lowest possible energy. Okay, that is actually a nature. Okay, for example, we always like to lay down. We always like to sit. We always want to minimize our energy output. Nature is doing the same thing. So how to actually do that? In order to actually to dissipate the energy, you want to have all different ways for the molecules to dissipate energy. When you see this word random, what it really means is actually it has a lot more different ways for you to actually dissipate the energy. Let's do a simple example for you. Assuming you have two balls, okay, one is yellow, one is blue, and they have two containers. Then I say, okay, then randomly put the balls into your containers. The possibility will be, if you would put two on the same containers, that's one possibility, right? The other possibility is actually you put yellow in the left, blue in the right, or blue in the left, yellow to the right, or you can put both on the right. So if you have two containers, there are 4 different ways you can actually put the balls in, right? So you have 4 different possibilities. Okay, everybody follow this? Okay, so now think about this. Every time when scientists says, okay, it's more random, what it means is I'm increasing the number of containers I can have. We know if you have 3 containers, then you're still putting the same energy. Okay, that those balls represent your energy. So you start to put your energy into different box now. So the way you can put it now become, okay, you can put yellow, blue on the leftmost. You can put yellow, blue, or yellow, blue, or blue, yellow, or yellow, blue. So this is a go on. So if I say something's getting more random, what I really mean is actually it has more ways to actually dissipate your energy. So since you have more ways to actually dissipate your energy, you got higher chance to become more stable. That's actually the really meaning of the randomness. Okay, that just indicate you have a more way to dissipate your energy. Therefore, you maximize the possibility that it can happen. If you can actually maximize the possibility to distribute your energy, then this thing will probably happen spontaneous, because right now the possibility you see that thing to happen become very, very high. So that's the physical meanings about this randomness, or about this term entropy. So now let's talk about something that's more relevant to your homework. If a substance exists in different phases, then the gas phases is going to give you the largest entropy, then the liquid, then the solid. So I want to actually make a very strong emphasis that the gas has way larger entropy than your liquid, and then way larger than your solid. So let's actually the first concept that you need to know for this slide. And we're going to go through a few examples. First one, in your homework, it's going to asking you whether the reactant or the product side has a larger entropy. From here, you know the things that really matters, that contribute the most to your entropy will be the things in the gas form. So the way you handle this type of questions, actually, you count how many gases you have in the reactant and product side. Whoever has more gas, that side is going to have a larger entropy. Let's look at these examples. You count number of mole of gas you have on the reactant and product side. Here you have 2 moles of gas on the product side, right? You have 1 mole of gas on the reactant side. Since you have more gas on the product side, the entropy of your product is going to be larger than the entropy of your reactant. You can just ignore the solid, you can ignore the liquid. Okay, the things that matters is actually the gas molecules. Second example, 2SO2 gas plus 1 O2 gas give you 2SO3 gas. Which side has larger entropy? Reactant or product? Yes, so the entropy of your reactant is going to be larger than the entropy of your product. How about the third one? Reactant, right? You can cross out your solid form, right? So entropy of your reactant larger than the entropy of your product. Another thing you're going to encounter here is that if I just tell you, I have a species at 2 different temperatures, and ask you which one is going to give you a larger entropy turns, it will be the one with higher temperature. The higher temperature one is going to give a larger entropy turn. So it's actually a T delta S turn. Okay, so let's actually the second things that you need to know. Third things that you need to know for this part, it's going to give you a bunch of species and ask you, can you rank all these species based on its entropy? For example, here I give you this 4 different species. And then I will ask you, can you actually rank these 4 species based on its entropy? In general, it's actually gas larger than liquid, larger than solid. So you know here, this one should be the smallest one. Then it should be the liquid one. So right now we have 2 things remains. One is SeO2 gas. The other one is SeO3 gas. So which one is going to give you a larger entropy? To answer these questions, it's really becoming, okay, you want to see which species give you more atoms. The one that give you more atoms, they have more way to actually distribute their energy. So in this case, you should see that since SeO3 has more atoms than your SeO2, SeO3 has larger entropy than your SeO2. The take-home message here is actually that if you have a more complicated molecule, you are going to have higher entropy.